It's my pleasure to introduce our speaker today, Kelly Miller. Kelly did her undergrad work at McGill, after which she spent a year on the pre-mastered fellowship in Concordia, teaching a captive audience of some 50 students physics. Some of you may remember that a couple years back that she actually sank off the coast of Brazil. Those of us who know Kelly are somewhat suspicious that she was maybe connected in some way, but so far there hasn't been any. So anyway, she got her Master's of Science in Teaching from our department here at UVM. That's how we know her so well. After she left us, she stayed here in town and taught at the Gaylor School for a while, and then she went up to Montreal to study private school for 3 years, and there, among other things, she coached a physics team to the Weizmann Institute in Israel. They got to go over there twice and participate in an international physics safe-cracking competition. And I think right off the bat they took home, what prize? First prize, yes. So they took first prize home, and then I think third prize.
Thanks for all your help.
Well, I was just, anyway. But, so anyways, that was, Kelly likes to travel a lot as well, as you might guess. Somewhere along the way, she also got an MBA from McGill. I'm not sure where that fit in, but she's got one of those too. She's currently at Harvard in the Applied Physics program, and she's going to talk a little bit today about her research. And before I forget, here's the coveted gift that everybody comes here to get.
Thank you.
Yeah,
Thanks a
I
lot.
think it's the multiple.
Thanks a lot. Well, I wanted to start by thanking everybody for inviting me, and I still really miss the physics department here, and it's great to see everybody again. So thanks a lot for the invitation. It's a huge honor. So as David mentioned, I'm in the Applied Physics department, and I'm working in Eric Mazur's group. Mazur group does two different sort of types of research, nanophotonics, and then also physics education research. And on the physics education research side, the group focuses in two sort of main areas. The first is understanding how specific pedagogies affect conceptual change in students. And the second is implementation of interactive teaching strategies. So given those two different aspects, I've divided this talk into sort of two distinct sections to represent each of those areas. So during the first half of the talk, I'm going to talk about some research in lecture demonstrations. Part of the data was collected here in the department. I did a pilot study in Jason Pepe's class, and then subsequently went into Calvin's Physics 31 class and collected a bunch of data there. And so that made up exactly half of the data that went into that study. And then the second half of the talk, I'll discuss a new class that's being offered in the engineering school at Harvard called Applied Physics 50. And this is a class that's been flipped, and I understand that the department here is thinking about implementing some studio physics, so I thought I could provide this as an example and answer questions that you might have about the implementation of this particular course that's in its second year of being run. So, okay, so for the lecture demonstrations, so the focus of this project was to understand the role that lecture demonstrations play in student learning. And as we all know, demonstrations are an integral aspect of introductory physics classes. But there is a lot of research out there that indicates that students actually learn very little from demonstrations, and that demonstrations sometimes serve to actually strengthen students' misconceptions. Another thing the literature tells us is that the teaching method matters when you're presenting a demonstration. This is a figure from a 2007 paper that actually came out of the Mazur group, where students were divided into sections, and the demonstrations were presented over the course of a semester in the section using 3 different modes of presentation. So in the least interactive mode, the observe mode, students just passively observed the demonstration. And then in the second mode, the predict, they were asked to first predict what they thought would occur during the demonstration, and then watch it, and then hear the instructor's explanation. And then in the third, the most interactive method, students were asked to predict first, see the demonstration, discuss amongst themselves what occurred, and then listen to the instructor's demonstration. So those three different modes, were maintained for the entire semester. And then at the end, students were asked, as part of their final exam, what did you observe, during these demonstrations? And so this plot shows the rate of correctness on those particular questions compiled for the three different modes, and it compares to students who actually never saw the demonstration. So there were some students who just were absent and they were pulled together, and then compared to the three modes. So a couple of things that came out of this, a couple of interesting things that came out of this study is that the observe, the passive mode, was only marginally and not statistically significantly better than the students who didn't see the demonstration. So indicating that if you're just sitting there passively watching it, it's almost like you never saw it at all. And then the other thing was that the predict mode, making a prediction seemed to be the most important sort of element of the pedagogy in terms of being able to report at the end what occurred. And then the most interactive was a little bit better than that. But making a prediction, at least from this study, showed the most significant sort of improvement in what students remembered. So given what this paper showed, we sort of focused on that most interactive mode of presenting demonstrations. And we wanted to delve into that further and see specifically what roles the predictions play. And secondly, what role does a student's prior understanding, before seeing the demonstration, play in what they sort of observe and then subsequently remember from the demonstration. So those are sort of the main two. Yeah.
I just have a quick question. I mean, that's great results, but it seems like the discussion would take more time than the other one. So how did they manage to cover the same material in these sections within the same time?
Yeah, that's a good question. So they did. It's true that the discussion section did spend more time, but you could argue that you remember it more because they
No, I
spent
wasn't
more
arguing
time.
that. I just know how they physically fit it into the same class period.
Well, so this particular study was done in section. It wasn't done in a lecture. So it would have been a component of a section that, so they would have just spent more time. They would have spent less time, asking questions. The section was comprised of this study and then also students asking the teaching fellow questions. So I guess they would have shortened that part of it. I wasn't involved in this particular study. This is sort of just background to the study that we ended up doing. But so yeah, sorry, I lost my train of thought. So yeah, given the fact that this is the most, we focused on those two questions for the study that we did. So in terms of the outline of this portion of the talk, I'll first just describe the method that we followed, and then go through some of the results, and then just talk about some instructional implications for demonstrations and doing demonstrations in classrooms. So in terms of the data, I mentioned that collected data in two different classes. It ran it as a pilot in Jason's class, and then in Kelvin's class collected data from mechanics demonstrations. So there were 201 students in Kelvin's class, and then the other class I went into my advisor's electricity and magnetism class at Harvard. So we collected data from 10 different mechanics demonstrations and 12 different electricity and magnetism demonstrations. And for each of the demonstrations, students' responses to questions were collected at several different points in time, both before and after the students saw the demonstration. So this is sort of, it's a little bit, the method that we followed is a little bit confusing, so this is just to sort of help you keep track of all the different questions that we asked at different points in time. So before the demonstration, before the students were introduced to the demonstration, they answered 3 to 4 conceptual questions that were designed to establish like a baseline of their understanding of the underlying concept behind the demonstration. And then we asked students to predict the outcome. So like the instructor would sort of like introduce the equipment, say this is what I'm going to do. Then we'd ask the students to predict. Using like clickers in Eric's class and in Kelvin's class just on a piece of paper. So this is an example of one of the predict questions that we asked for the electricity and magnetism, one of the electricity and magnetism demos on Lenz's law. And then the instructor would do the demonstration, the students would discuss it, and then the students would listen to an explanation from the instructor of like as to what they saw. Then after the demonstration, like later that day, students were asked, so like after they left the class, but later that day, students were asked 3 different types of questions. So a multiple choice question asking them what they observed, so just like, what did you see? And then also a free response question asking them to explain their understanding of the physics behind what they saw. And then a few sort of analog questions, like conceptual questions that were similar but not the same as the prior knowledge questions that were asked before the demonstration. So those like kind of post-knowledge, like what we call post-knowledge questions. And then at the end of the semester, we asked the same 2 sort of like questions. And in the context of like the end of the semester, we're calling it like remember. Like what do you recall the demonstration where like what happened? So because it's at the end, we're calling it remember instead of observe. And then also use your understanding to explain what happened. Okay, so that's the method. So in terms of the results, we found sort of 3 main things. So the first is that the students who correctly observe a demonstration have a higher conceptual gain when you compare those pre and post questions. So if you take a student, I say at like a 0.4 level on the pre-conceptual test, and you follow it up to the first line, the students, so the bottom line represents students who did not observe the demonstration correctly. So they have like a lower level of post-conceptual understanding than students who did observe the demonstration correctly, which is the top line. So you can see that at a given level of performance on the pre-test, students who observe the demonstration do better on the post-test. Going back to the initial goal, which was to learn more about the role of predictions in student learning, we can see that students who make a correct prediction observe the demonstration, or students who make a correct prediction, right, the bar on the far right, observe the demonstration correctly at about an 80% level, which is, it seems high, but if you think about it, if the question is being posed like within a day of them actually having seen it, instead of the other study where it was at the end of the semester, which means that 20% of the students within a day of having seen the demonstration do not report having like seen the right outcome. And another interesting thing that we found is that there's no difference in the rate between students who predict correctly and students who predict incorrectly. So a hypothesis that we had going in was that if you make a prediction and it's wrong, that you'd be more likely to sort of notice the correct outcome because you'd be surprised, or you'd be sort of you'd be more likely to stick in your mind. But that doesn't seem to be the case. Students who observe incorrectly observe at approximately the same rate as students who predict correctly.
So sorry, this is not observing incorrectly, this is predicting incorrectly, right?
So this bar is for like students who predicted incorrectly, and this is the rate of observing correctly on the y-axis. So another thing that the study showed, but was really only confirmed from the last study that I had mentioned at the beginning, is that there's a huge difference between the group of students who didn't predict at all and students who predicted. Right, so students who like failed to make a prediction observe at a considerably lower right, observe correctly at a considerably lower rate than students who make a prediction. But that's really just confirming what the literature already said. Okay, so those, and then the third thing that we found, like looking at the prior knowledge aspect of the study, is that students who know more physics at the time of seeing the demonstration are more likely to A, observe, and B, remember the demonstration correctly. So this plot shows, like, we grouped students into 3 groups according to how they did on this series of questions. So we had like a below average, average, and above average group. And we looked at the rate at which those students answered the correct outcome question initially, like right after the demonstration, and then on the right at the end of the semester. So the higher the student, the better the student's understanding when they see the demonstration, the more likely they are to like sort of take the right cues, like, you know, discern what's going on when they're watching it, and the more likely they are to remember the right outcome at the end. So putting those 3 things together, so this is just a schematic to sort of see how those 3 plots fit. We found that to be able to sort of gain something conceptually from a demonstration, you really have to observe it correctly in the first place, which just makes good sense, right? But there are 2 factors that go into observing a demonstration correctly, and that is making a prediction regardless of whether the prediction is correct or incorrect, and also having some level of conceptual understanding before seeing the demonstration. So in terms of how this fits in, like, into sort of an instructional setting, we came up with like 3 recommendations, and Calvin and I wrote a paper on this for physical review special topics. And these are the sort of 3 like conclusions that we came up with in terms of for instructors who are doing demos in their classrooms. So the first is the obvious, which is make sure that the students correctly observe the demonstration in the first place. So you could do this by, you know, having someone in the class like summarize what they saw, or having students report it down, or, and you know, the discussion part of the demonstration is important for this reason as well. So just making sure that the outcome is like reiterated and not just moving on to the next thing. The second is having students predict, you know, for obvious reasons. And the third is to do the demonstration at the right time. So to time it properly. It's not a good idea to use a demonstration to introduce a topic that students don't have any sort of conceptual basis for, you know, which is often done, right? Students have no idea sort of what to even look for it, especially if the demonstration is really complicated and there's a lot of things going on. They're unable to like separate the signal from the noise. So to sort of use a demonstration to reinforce a concept rather than introduce it. So that sort of like covers the first aspect of my talk. I think maybe, yeah, I'll take some questions if you have questions, and then move on to the second part since they're so distinctly different. Yeah?
So the predict question you had up, the drop a magnet through a pipe, students, if they haven't already seen Lenz's law, totally going to be flummoxed by that.
Yeah.
But it's one of those really fun, like, we can do this, and they're totally confused.
Right.
And so from an engagement in the class, from a theatrical standpoint of getting their attention off their cell phones, that's often held up as here's a great demo that makes students go, what's going on?
Right.
And try and get them to engage. And you're saying, teach them Lenz's law, give them the equations, do like a week of that, and then right before the test, actually drop the magnet through the pipe?
Well, yeah, because, I mean, so they, dropping the magnet through the pipe, I mean, it's cool, right? And it grabs your attention. But during the explanation, if you don't have any idea of Lenz's law, you don't appreciate the explanation of what's going on. You know, like the explanation is totally lost on you. So you might remember the outcome, but for the wrong reasons. You know, and I didn't get into it because I wanted to spend more time on the second part, but the explanation part of those 2 questions, the rate was like shockingly low. Like there are a lot of instances where people remember the right outcome because it's a multiple choice question, right? But then their explanation is just like completely, like they have the right answer but for the wrong reason. Yeah.
A few slides back, you had increase in understanding whether or not they predicted it correct, or whether or not they actually observed it correctly. And it seemed like people who didn't observe it correctly still got a bit better. Was
Are you talking about the? Do you want me to go back?
the diamond versus
Yeah. Oh yeah. Yeah. So I mean that might be a test effect, right? Like because the questions, while they were the same, the conceptual questions, the pre-post, while they were the same, they were similar. So yeah, I mean you could still observe it incorrectly and do better on the post test because you've answered some similar questions and you've also learned a little bit, presumably in the class.
So presumably they understood a bit of the discussion, even if they don't
Maybe.
remember the
Yeah.
topic correctly.
Yeah. Right. That's a good question. Yeah. Okay. So, are there any other questions? No. Okay. So this is the second part. This is Applied Physics 50 is a class that I've been involved in for the past 3 years. I spent 1 year helping my advisor develop it and come up with sort of the curriculum, and then for the last 2 years I've been involved as a teaching fellow. So the structure of this talk, again, I'm just going to go through a little bit of the background of Applied Physics 50, talk about like the team and project based elements of it, and then some of the structure and logistics of like how we set the course up and like some of the assessment tools, and then the results, like whether so far it's working, like how it's working so far. Okay, so Applied Physics 50, it's an example, well it's a new class that's offered to the undergraduate engineering students. It's a two-part course. It's introductory mechanics in the fall, calculus based, and in the spring it's intro E&M. And it's twice a week for 3 hours, so 3-hour blocks, and all of the elements of it are integrated into those 3 hours. So there's no lab sections or tutorials. There's office hours, but like all of the components are within those 2 3-hour blocks. And it's an example of a flipped class. So there are no lectures. Students are expected to read the textbook at home, develop a certain level of understanding of the material before coming to class. And then in class, they work on problems and engage in different activities that are designed to help them learn the material. So I'll explain a lot more about how this works in the structure section of the classroom, but basically it's like what you would traditionally do in the class, like the sort of lecture, is students are sort of doing the equivalent, or what we think is the equivalent, outside of class, and then in the class they're doing sort of the more homework, like problem solving, working with groups and working in teams. So the students, last year was the first year that it was run. It was capped at 35, so it was like pretty small, and this year it's grown to 91. Most of the students are in engineering sciences, and most of them are sophomores and juniors. So in engineering sciences, you don't have to take physics in your first year, whereas so this would be a course that would physics majors would not be allowed to take. They take a completely different class in their first year of the program. So it's modeled after the TEAL class at MIT. So TEAL stands for Technology Enhanced Active Learning. And we spent, in the development phase of the class, we spent a semester observing classes at MIT. And the classroom that was ultimately sort of built to accommodate this course was designed sort of like loosely based on this model. One major difference is that the MIT has a lot more technology, whereas we have almost no technology. So the space that we use looks like this. So it's similar in that there are whiteboards around the room, like that they're on rollers. And all of the tables and chairs are like on rollers also, and the tables can be configured into like a lot of different ways to accommodate different size groups. And it's really simple. There's no technology at all aside from the overhead projector. Whereas the MIT, like everything is wired, and the labs all have these like micro-based computer systems, and it's so this is a very low-tech version of the Teal classroom. And the main thing is that the room is like very flexible and conducive to teamwork. And teamwork is really like the focus of Applied Physics 50. The students are organized into teams. They come up with like names for themselves, and they do all of the projects and the classroom activities as part of these teams. So like the whole class, they're sitting like around those tables as part of a group that is semi-stable. I'll talk a little bit more about the groups in a second. So the semester, so this is an example of what the fall looks like. The semester is divided into 3 projects that last approximately a month long each. So, and each time the students are grouped with a different group. So like, they're working as part of 3 different groups over the course of the semester. And each time, so like, a lot of, if you read research on team-based or project-based learning, a huge component of that being successful is having well-balanced groups. So we've been experimenting with different group formation techniques. And so in the fall, the first group, we base it on the students' incoming scores on the force concept inventory, just to make sure that there's not one group of students that has like all of the physics knowledge and one group that doesn't have any. And then the second project, we have them take a survey that sort of like quizzes them on on their learning styles. And we construct the groups so that there's a variety of different types of learners. And then the third group, we have them write a proposal. So the third project involves designing and building a zany musical instrument. And so we have them write a proposal, and then we group like-minded proposals together so that they're working, sort of in big musical instrument areas that they like. So here's a copy of the schedule from the fall, and I show this just to emphasize the fact that all of the classroom activities, and I'll talk more about the classroom activities in a second, but all the classroom activities revolve around these 3 projects. And the reading, so like the students have to read specific portions of the textbook before coming to class, and the reading is all designed to sort of help them with whatever activity they're going to be doing in class. The activities are sort of focused to help them with the project that they're also working on concurrently. Yeah.
And are you doing pre-class quizzes online, or how are you enforcing the reading?
Not pre-class quizzes, although I think like we would ultimately like to, after talking to Dr. Spartali, like we would like to try and move that way, but we just didn't know about like what system to use. But I'll show you what we do for pre-class activities in a second.
Yeah, is the textbook something specialized to this
Yeah,
format?
so the text, yeah.
So I wouldn't recognize what all those chapters are necessarily.
Right, so the textbook is, so Eric Mazur wrote a textbook, like has spent the last 20 years writing a textbook, and it's finally finished.
Yeah.
And so he wrote it sort of specific in an order that, like with conservation principles first. So like, yeah, he uses his own textbook, which is part of the reason why, it works this way.
Okay.
Yeah. So, okay, so at the end of each project, there's a symposium, and each group is required to present and demonstrate whatever project they have been working on. And so you can see on the left a group demonstrating their group Goldberg machine, and on the right another group demonstrating the musical instrument that they designed and constructed. And I have a video from this year of one of the Rube Goldberg machines. So the project was designed to, so at the end, they had to design a machine, design and build a machine that would crack an egg. So the last step, I don't know if you can see, but they fling like an egg at this like bale of, sort of board of nails. Like, so that was one of the better ones. Okay.
The janitors love that.
Yeah, it was pretty messy. Okay, so now that you've seen like an overview of the project and the team-based elements of the class, I'm just going to go through some of the structure and the like general logistics of how it's set up. So before class, students read and annotate a textbook online. So like Eric's textbook is uploaded to this website that I'll describe in a second, and students are required to read it and like highlight it, and then make comments and ask questions about it. So I'll talk about that in a second. And then in class, students are doing like a variety of different activities. So there's some peer instruction, some problem solving. So like a lot of the problem set, students are actually doing in class instead of at home. Some experimental design activities. The University of Washington tutorials. They're given some time to work on their projects. So there's some like unstructured time where they can get together with their team and work on projects. And then assessments. So I'll talk about the assessments in a second. So the peer instruction activity, I think most people are probably familiar with how peer instruction works. The instructor will present a conceptual question, and it's traditionally been like a multiple choice question, such as this. Students will use like some sort of personal response system to answer the question, like a clicker, to respond to it individually first. Then students are given the opportunity, without being shown the poll, students are given the opportunity to turn and like discuss the question with the people that are sitting closest to them. And then they're told to, after the discussion, to re-vote. So this would be this is a system that I'll describe in a second. So instead of using the personal response, the clickers, we use another system called learning catalytics. But this would be, like what the students would see is on the right-hand side. So they're all using devices like laptops or tablets. So the question pops up on their laptop. So they see this. They respond by clicking on what they think the answer is. And then this would be what the instructor would see at the front of the room. So like the polling doesn't appear to the students, only to the instructor. So I mentioned that we don't use clickers. Instead, we use this online cloud-based system that was developed by one of the postdocs in the Missouri group called Learning Catalytics. And one major advantage to learning catalytics over clickers is that the instructor is not restricted to asking only multiple choice questions. So here's an example. It doesn't really show up super well on the screen, but here's an example of a question where students are asked to indicate the direction of the vector sum of the forces that are acting on the central charge. And so if they're using a laptop, they would just like click with their mouse and drag. If they're using a tablet, then they would just sort of drag their finger across the screen. And you can see like this is what the instructor would see. So the 2 rounds of questions, the individual rounds, you can see that like quite a few of the students, almost half of the students thought that the vector was going in the opposite direction. And then after having had the chance to talk to their neighbors, they were 100% right in the second round.
Is that software available public domain?
Yeah. So it was just recently sold. The software was just recently sold to Pearson, so now it's offered, I think, as a package with textbooks, and I think you can also subscribe, but it's not free. Okay, so that's the sort of peer instruction part of the class, and so this activity would happen for 90 minutes every 3rd class or so. So about twice a unit. There would be like a 90-minute peer instruction session. Yeah.
And how many questions do you get through in that?
About 10 to 12. So it's not super fast. It's like, yeah. Okay. So the experimental design activities, I mentioned that all of the components are integrated into the 1 3-hour block. So there's no lab, so this would be like the closest thing to a lab. So in some cases, it's like this, where they're manipulating like some sort of a simulation. This is a PhET simulation from the UC Boulder group. All of these simulations are free, and they're really great. The picture on the right is another electric field hockey simulation that's fun to play with. And then sometimes we have equipment, so they're working at their tables, and if we have equipment and we're asking them to sort of like, we've given them a bunch of stuff, a bunch of different types of things that they can manipulate, and then we're asking them to use all of them or some of them to build like some sort of a thing, like a galvanometer. So that would be instead of the lab. So now that I've given you an overview of like some of the types of activities, those are just a couple of examples of activities that are integrated into the in-class part. I'm just going to speak briefly about how the actual content is delivered. Because remember I mentioned that there's no lecture, so like all of the class time is taken up with activities. So the students access all of the textbook content via this system called NB, which is free. It's an open source piece of software that is on the MIT website. So a PDF, the textbook in the form of a PDF, is uploaded to this online NB site. And this is just a website that students log on to, and they read the text online, ask questions about what they're reading, and then respond to other students' questions. And the instructor can log on and see what kinds of questions students are asking about the material, and it's used sort of as a replacement for just-in-time teaching. So like the instructor can go in and see like what the problem areas are, and sort of like maybe pick concept test questions that will address those like problems. So because of the collaborative nature, like students asking and answering each other's questions, it's like referred to as a social annotation website. It was developed by this group in the computer science department at MIT, and yeah, it's just a mechanism for students to ask and answer each other's questions, and also for the instructors to interface and sort of provide feedback as well. So this is what it looks like. It's not the most like visually pleasing software. The textbook. So this is an example of a page from the textbook on the left, from one of the electricity and magnetism chapters, and then on the right you can see that. So it doesn't show up well because I don't know, the screen doesn't show it, but this particular student that's written this comment has highlighted like a little box of text right here, and then has said like, I'm confused about this, da 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 da, and then each of these is an individual response that another student has made to try and answer that question. Yeah.
Does the software keep track of who is asking questions and who's answering, and sort of tally up for you whether they're actually doing the readings?
Yep. So there's a spreadsheet where it gives you almost like a grade book type thing of like the students down like one column, and then the number of annotations that they've made for each chapter. Not the quality of the annotations, but just the number. Yeah. So
What if a student responds to a student's question incorrectly?
Yeah, so
That's out there for a while,
right,
until the instructor gets it.
Yeah, so that happens all the time, but normally what happens is another student will go in and correct them before we have a chance to even notice it. So like it's almost like a self-monitoring system. And then, I mean, one of the teaching fellows' jobs is to go through and sort of like skim them, and if there's something glaringly and like, you know, leading people down the wrong path, then an instructor will intervene. And there's also a mechanism where, so you can see in this thread, the student has like put a question mark indicating that they want like an instructor to intervene. So you can see like this is the question, and then somebody else tried to respond to it, and then Eric eventually went in and like put a response. So the student can request some sort of instructor feedback. So that's how like right now how we're doing it outside, like the pre-class that you were asking about. So in terms of the assessment, yeah.
Is the instructor also present during the 3-hour blocks?
Yep. Yeah. There's also there's the instructor and then a bunch of different a bunch of teaching fellows. So just walking around and helping people.
What kind of ratio of teaching fellows to students?
So this past semester there were 91 students, and then there's the main instructor, a preceptor, sort of like a co-instructor, and then 3 teaching fellows. So kind of a lot. Yeah, like 5 to 90. Yeah. Part of that is because it's a new course, and it's given more support than like another course would be. I suspect that once it runs a couple more times, that the ratio will increase. Okay, so the last feature that I'm going to talk about is the assessment. So there's 2 main ways that the students are assessed. The first is the 3 projects. So there's a rubric. The students are expected to present, their project, and then also hand in a final written report where they're asked to sort of figure out the calculations behind, the Rube Goldberg machine. And so they're assessed on both the presentation and the written report. And the second is something that is called a readiness assurance assessment. And this is adapted from something in team-based learning called if-at assessments. So I'm just going to describe if-at assessments and then describe how we've adapted it. Yeah.
Okay, so back to the projects. Do they get a group grade or is it an individual grade within the group?
Okay, yeah, so that's a good question. So they get a group grade on both elements, both the presentation and the final report. But then there's also a peer assessment. So they assess each other. There's an online system that they log on to. So you see other people, when you log on, you see the other people on your team, and you're expected to rate how your teammates did in a number of different areas. So were they punctual? Were they, different, did they contribute good ideas? Were they always ready to help, when something needed to be done, that kind of thing. And so each student receives a score that is sort of a composite of their, what their team gives them. And then their project grade is kind of prorated. It's like an index. So if my team thought I was a terrible group member, I might get a 0.5. It's like an index. And so I would only get 50% of the project grade. So each group gets a grade, and then each individual gets a grade based on what their team thinks of them as a team member. And then my grade, so everybody has a final project grade that is different and dependent on what their other group members thought they contributed. So that part is still being worked out because the students hate it because they feel as though they're I don't know, it becomes it sort of messes with the dynamic of the group a little bit because they feel like they're being judged by each other. But in any case, we're still working on that. So, okay, so going back to the readiness assurance assessments, so how if-at assessments work in team-based learning is students are given a multiple choice exam, and there are 2 parts to it. So they take the exam first individually, and then hand that in. And then they sit down with their team, and they have the same exact exam, and they're given a scratch card that might look something like this. And the scratch card is coded or with the answer key. So if these 10 questions comprise the test, question number 1, you can see the group has to decide as a group what they think the right answer is, and there's only 1 scratch card per group. So they're handing in the scratch card at the end. So for question number 1, you can see that the group scratched off the right answer in the first go. Okay. For question number 2, you can see that they initially scratched off B, but that wasn't correct because it didn't have a star. And then they get another try, and they scratched off A, and that turned out to be the right answer, and you can see that their score is discounted. So they only get half of the value because it took them 2 tries to get the right answer. And you can see with question number 4, it took them 3 tries, and so they only get 1. And so it becomes like an exciting game where they have to sort of discuss each question and come up with like a group answer. And then their grade is 50% of their individual score and 50% of like what their team gets as a score. So we've adapted this idea to work in conjunction with learning catalytics because the major drawback to this is that you can only ask multiple choice questions because of the constraint of the scratch card. So maybe before I get into how we adapted it, this is just the philosophy behind it. So the fact that research has been done on this and it's shown that it's beneficial because the students are getting immediate feedback instead of having to wait a couple weeks before they get their exam back. The research has shown that students learn through testing. Like testing yourself is a good way of sort of learning. And then finally, the fact that students are leaving after having established what the right answer is. They're not going away. Like when you take a normal test, you might put the wrong answer in, you go away, and then depending on how vigilant you are when you get the test back, you might never find out what the right answer is, right? Because you've long since cared once you get it back. So the fact that you leave the room knowing what all the right answers is like very beneficial. Okay, so how we use this technique in Applied Physics 50 is it's equivalent to like an exam. So there are no like traditional exams in Applied Physics 50. Instead, we use these readiness assurance assessments. And we use the same idea, 2 rounds, an individual round and a team round, and same 50-50 split. So the students are answering, I'll show you what it looks like. So they're answering between, 8 and 15 questions. And they're doing it on Learning Catalytics, so on that online system that I described. So they're sitting and they're not talking to each other and they're just answering the questions on their computer. And then the system records their individual answers. And then the second hour, these traditionally take 2 hours, they log on as a team with a team name. And they have like one person that they've designated as the inputter. And then that person like inputs the team's responses. And they get the same, they get 3 tries before the system eventually just tells them what the answer is, at which point they get 0 for that question as a team. Yeah.
So you were putting forth that you organize teams based on course concept inventory scores for the very first run. And so all these students go and take their individual test, and then they sit down together as a team, and one of them in that group has a better physics knowledge than the other 2. Mm-hmm. So how do you make sure that they're actually having a discussion and actually everybody's learning versus this person says, well, I've got this, and just puts the right answers down? Because they'll figure out amongst themselves who has it and who doesn't quickly.
I mean, it takes them a while to figure that out, and like if you don't necessarily know what everybody's.
You don't know that you're the high or the low or the mid.
And a lot of people, I mean, at least from an observer's point of view, will appear very confident of the answer and actually not be right. It's not just based on like how much you know. Like confidence and actual knowledge don't always go hand in hand. So I mean, I think like there's a period of time where the dynamics are playing sort of an interesting role where like somebody's like, I've got it, and then they don't, and then like they never believe them again. Right? Like so like it is dependent on I think personalities as well as like.
And do you get blowback from the students that their grade is being based on other people's?
Well, I mean, so what happens is the individual score is very, very low. Like the average for the round 1 is like somewhere between 50 and 60%, because we try and pick questions that are hard enough that the discussion is going to be interesting.
Mm-hmm.
But the round 2 is usually like or very close to it. So usually it's a question that is hard enough for them not to get as an individual, but easy enough that after the discussion they get it. Because that's the whole point. Like the point is not necessarily to rank students against each other. It's as an exercise, like it's seen as another exercise for helping them learn. Yeah.
Seems like you could protect against an issue like that by just saying you're going to get the higher of the 2 grades, because if they ace the first one and the rest of their team says no, it's wrong, you would hate to bring them down.
Yeah. So there actually is somebody in our group who's doing research on that very question, does being in a group disadvantage super smart students? And they found that there's never a case where the highest individual score is higher than the group score. We've never seen that. It's always the same, or the group score is considerably higher.
You're doing a peer comparison, or just an overall average?
We're looking at it case by case. We've never seen a single case in the 3 semesters that we've been doing this where a student has scored high individually and has been disadvantaged by their group score. Yeah.
How do you deal with timing on the group part of the exam?
So it's timed to be an hour for each, and at the end we just cut it off.
I'm just curious in the group parts, do you often see groups having difficulty with time management, like discussions that run too long because of disagreement?
Yeah, but so the first one is a disaster. Some of the teams only get half of the questions answered, right? But then they sort of learn how to pace themselves. The other thing I forgot to mention is the system is set up in such a way that when they log in as a team, they can see how each individual person in the team answered. So if the 4 of us were all in a team, it would say Kelly, and then my answer, Dave, So we can either pick one of those or put in a totally different answer. Yeah.
How does this work when you're doing a mathematical style problem where you want to be able to show the work and show the process?
So that's a huge disadvantage of it. There are no points given for steps. It's a binary, either
and that's
it's
for
right.
all the tests, or is this one style test and later on you may have?
This is the only type of test we do. But you can see here, it's not they're not all multiple choice questions. This system has the ability to accept expressions.
Yeah.
So
like
algebraic expressions.
Kind of like the online loops in the edX style.
Pardon?
Kind of like the edX style software.
Yeah. Yeah, and it'll also do numerical and ordering, matching, different types of questions. Yeah.
It would seem that one of the really crucial points in this is that the students have looked at the material before class.
Yeah.
In most lecture courses, they don't look at it until just before the exam.
Right.
If that.
And how do you control that, and how do you avoid students who just loaf?
Well, so I mentioned that 50% of the grade is their grade on the projects, and when the other teammates are evaluating the students, because the various activities are sort of integrated into the bigger projects, they're also evaluating how their group does in the other components of the course. So if I had never read a single thing before coming to class, I would presumably be a really bad person to have on a team, doing this activity, for example. I wouldn't be able to contribute much to the team score here.
Peer
so
pressure.
Right. So it's peer pressure, I guess. Yeah. Yeah, but it's not working perfectly. I still believe there are a lot of students who come having never read a thing. I think that's always gonna happen. Yeah.
So you say no exam, not even a final exam that
No.
tests what they got? Huh.
This is the only form of sort of exam that we do. Yeah.
One other question. Have you, or can you in any way, control for what's known as the, I forget the the proper name, but the kids know that they are a special group. This is a special course. And how do you avoid the Hawthorne effect?
Oh, I see. Yeah. You mean in terms of like the research that we're doing? You mean from a research point of view?
Yes.
Yeah. I mean, so
What effect is he talking about?
like the test, like the idea that you know that you're part of a test and you might change your behavior because you know that people are studying you. So we try and make it not obvious that we're doing research on them at the same time as teaching them. I mean, it is a different a course that's designed in a different way, but there are, other courses. Like this is not the only course that, they're increasingly interactive, like teaching strategies. So I don't know if they feel like necessarily special. But yeah, I mean, I guess also that could be a factor that we can't really do anything about.
The school is throwing a lot of resources at it.
That's true. Yeah, that's true. Yeah. Okay, so my last little section is just like does it work? And I mentioned there are a number of people in the group that are sort of doing active research on this, and I don't have time to go into all of the different projects. But one way that we can make a quick comparison, at least from the point of view of students' conceptual understandings, is to compare students' like normalized gain scores in Applied Physics 50 to other classes that are offered at Harvard. So Harvard has 3 different tracks or streams or levels of physics. There's this like physical science 2, which is like just a general education, non-calculus based. And then there's this mid-level stream, which is calculus based, and this would be sort of the equivalent level to Applied Physics 50. It's traditionally like engineers and pre-meds, and it's being phased out of the department as more and more students are sort of like choosing this other option. And then the third stream is a calculus-based class for physics majors. So this plot shows on the y-axis normalized gain, which is just the post score minus the pre-score, but normalized according to how students did on the pre-test. So it's like post minus pre divided by 100% minus pre.
But I thought you said you didn't do a post-exam.
It's not an exam. It doesn't count at all for their grade. It's after the course is already over. It's like a conceptual survey. It's done in all of the classes there. Like students who take any type of physics class at Harvard are asked to do this pre and post test. And so these 3 bars are like 8 years of data sort of averaged together. So 8 years of PS2, like normalized gain scores averaged together. And the Applied Physics 50 is just this past fall, in fall 2012. So it's like a much smaller sample. But I mean, based on this, at least from a conceptual point of view, the students seem to be, gaining conceptually. Yeah.
What's the student's perception of their effort for their outcome? Like, if you had students who worked 3 times as many hours on a physics class, they would probably learn more. Where are they at on that?
Yeah, so I think that because the class is completely integrated into that 6 hours a week, it's not perceived as being more work than a traditional physics class. Because with a traditional physics class, you have the lecture that's 2 or 3 times a week, and then you have the lab and the section, right? And most of the work is done in class, aside from the reading, which and they're graded on. I didn't mention this, but they're graded on the quality of their annotations that they do in the textbook, and that's like a substantial part of their grade as well, to encourage them to actually read and annotate. But aside from the reading, they're actually doing nothing outside of class. So I don't think, and possibly some project work towards the end of the night before the deadline kind of thing. But like, I don't think it's perceived, Like I think one of the reasons why the enrollment like tripled from year 1 to year 2 is because it's like seen as possibly not as rigorous or time intensive as the 11th stream. At least that's my suspicion. Yeah.
Did you do all 91 in one section? I mean, one of the things it seems if you're scheduling 2 3-hour time blocks, it seems like you would run into a lot of class conflicts with other things, and just wondering how you manage that.
It's purposely scheduled during the same time as the 11th series, because students would usually opt for one or the other. So that's how you get around the schedule.
So you just have one section of this?
Yeah, there's only one section. Yeah, right. Yeah.
This is a rather striking graph. Can you control for what the kids actually do? What I'm driving at is the calculus-based physics majors are probably going to have come from Bronx High School of Science or something like that, and they know it all.
Right.
And if they even skip the course, they could probably go on.
Yeah, so
And
you're saying...
they don't, and so that may not be a measure of what the course has done or
Right.
what the student
That's a really
has
good
done.
point. Yeah, so like you're saying these students come in with a high like conceptual understanding already, so they have not as much to gain.
Right.
Right. So I don't have this plot in this series of slides, but I have another plot that shows like the bar, the pretest against this, and it's not completely due to high incoming scores. Like actually the incoming FCI score for 15A students is not significantly higher than 11A students. I think the reason why this is so, I mean this graph I think is misleading for another reason, and that is that the students who are in 15 are focused on a different, on sort of a computational, like more sort of less conceptual. Like these two classes and Applied Physics 50 all focus on the concepts as opposed to the
Problem
mathematics.
solving.
Well, Applied Physics 50 I think does focus on problem solving, but not maybe as mathematically difficult problems as the 15 students. Yeah.
Has there been any tracking yet comparing these different classes going forward to success rate in future classes?
No.
So we see that the calc-based physics hasn't had as many gains, but they may have mathematically had more gains. And
Right.
what was more important to go to the next level?
Yeah, no, we haven't done that. That's hard to do because we don't, like, they don't always take, you know, like, all of these students don't necessarily take something afterwards.
Okay.
In terms of physics, like, you know, this might be the only physics class that they take. Yeah.
Just to make sure I understand the PS2, well, the 11A, let's say, versus AP 50, are they having the same amount of contact hours in the 6 hours?
Approximately, yeah, because like when you add the tutorials and the labs and the lectures, it's approximately the same. I don't know in terms of like homework, like how much time outside of class, but in terms of contact hours, it's just about the same, yeah.
So who is the best problem solver here? If you look at the 15A, say, they have standard exams of the kind that everybody offers. If you gave that exam to the AP 50 students, and then you ask the 15A students to do whatever the AP 50 students do for credit, you just swapped
Right.
the assessment, who would do better?
Well, so I think they would do better, like depending on how you evaluate, like how you assessed it. Like
Give them the same stuff, except
same
you swap.
same assessment.
You swap, that's
Yeah,
right.
so I think the 15A, the problems that the 15A students solve, I don't think the AP 50 students could solve. Like they're just mathematically too advanced. I don't know that the AP 50 students are solving more conceptual problems. So I mean, from this, it looks as though the 15A students wouldn't do well on those.
So basically this is conceptual enhancement of the students' understanding and not as much problem solving that they can use as engineers.
Well, there is, I think the emphasis of the projects coming up, you know, like with the ideas and sort of designing the projects, there is some problem solving in that. And there's also another part of the course that I didn't discuss, which is a problem solving, like they do a problem set at home first, and then they bring it in and do it as a group.
One
And-
more question,
Yeah.
I'll shut up.
Um,
These AP 50 students who go on to their engineering classes,
Right.
how do they compare against the 11A students
Yeah, so we.
in those engineering classes? That's the interesting
Yeah,
question
that
to
would
ask.
be really interesting. We don't know
Right.
because it's too new, but
Okay.
yeah, that would
Thank
be
you.
a good thing to look at. Yeah.
The three groups that you have, as I understand it, the first one, you tried to mix them based on their level, is that
Yeah,
correct?
oh, for the
And then
projects?
Yeah, and then the other two were more like around topics or something. So I'm wondering, is there a difference? Like, is the group learning more effective if you have a range of abilities, or?
Yeah, so that's actually another person's research project, is they're looking at project outcomes compared to how the teams were formed. But there's, like,
You don't know the
we
answer.
just don't know the answer yet. Yeah.
Just coming back to this split between the conceptual versus calculational side. So, because clearly, especially for physics majors, but in general, the concepts are quite important, but it's also important to be able to do the calculational
Right.
intensive side.
Yeah.
Do you have something analogous to FCI that allows you to measure that? Because if you only look at the FCI, for example, then you
Right.
might go 100%
Yeah.
conceptual in the course because you get these huge gains.
Right.
But
So-
you have to, it's a question of how much are you losing in the,
Right. So
the calculational side.
one project that I was working on last year was I took the exams from 11A and I put the questions into the readiness assurance assessment. So we reused like the questions and tried to compare how the students from 11A did compared to the Applied Physics 50. And it was like, there was no clear, it basically worked out in the wash. Like some students, like, on one problem, the AP 50 students would do better. On another problem, like 11, there was no way of sort of figuring out like there was no clear winner in terms of the.
but you have are you thinking about having any sort of standardized measure for that, like the FCI? Because the FCI is great for the conceptual side, but it seems like I'm not aware of something that's
I
fairly
don't know
standard
of
for the
any
calculational side,
yeah.
which.
I don't know of any
Okay.
either, like that we could use. I mean, which is why we were trying it with old exam problems. But, it was also an issue because these exam problems were done in 11A on a piece of paper, whereas we used the online system in Applied Physics 50, and so that wasn't a fair comparison maybe. So it changes the question when you ask it online. So, yeah.
Just want to echo Sarkalian's idea that if you go to statics for the mechanical engineers and you grab a subset of each prep from physics, you probably have a control experiment.
Yeah, that would be really, that would be a good thing for the next graduate student to do. But, yeah.
I'm worried about the textbook online thing. The fact that was collaboratively annotated. Do they have a copy at the end of the semester that just has their own annotations on it so they
No.
can use it for reference?
No, that's something that they, in the course evaluation, that they were all asking for, but the system doesn't allow that. That would be a really good feature.
Yeah.
Yeah.
I was wondering if you do any instruction at the beginning of the semester on how to work in teams. You just let them go at it.
We just let them go at it. The peer assessment part that I mentioned, where they're rating each other's like team performance, we do give them like a little bit of a background on how they should do that, like how they should think of it, and that seems to be a very like powerful tool for guiding people's behavior. Like we notice a huge difference between the first project and the second project in terms of how people work together.
So is there any research being done on that too? or
Yeah,
how that's-
another person is looking at like the peer assessment part and seeing like how other people's ratings of them like affect their behavior. Yeah.
I like the idea of how you did the other ratings of each other. One of the things I've done in some of my team projects that might be nice to incorporate here is they also rate themselves on all of those own categories. I was wondering if you do that.
Yeah,
'Cause it's nice. That way, people tend to own up.
Right.
If they were always late or didn't come, they know so then they feel less resentment because they owned up to it.
Yeah, that actually, I forgot to mention that, but we do have them rank themselves before they rank each other, because
Okay.
it's, I don't know, been shown to, you demonstrate more empathy if you're like ranking other people after having ranked yourself. Yeah. That's, any other? Yep.
I believe you said that the section that is analogous to the lab was mostly simulations.
Not, it's about 50-50 simulations and actual, like, little sort of experiments that they're doing at their tables. It's not as involved as a lab, but like when you go into an actual lab and you have sort of more elaborate equipment.
I was just wondering, has there been any comparison between physical examples and simulations? Because some things like E&M are a lot easier to see in simulations, but I've had some experiences with students where it is in essence a cartoon and laws of physics don't need to apply in
Right.
cartoons.
Yeah, and so I can't think of the journal, but there are definitely papers that have been written on that, on comparison between, and Lisa's doing some work on like video versus real life in terms of demonstrations, so, but I can't think of the,
I'm just wondering, once a course like this is really well developed, is there going to be pressure, like what do you need the instructor for anymore? A bunch of good TAs can handle this.
Yeah, so I think that is like an issue that we dealt with last semester because the scalability of it. Because last semester, the 91 students wouldn't all fit in one room. So we had another room somewhere like on the other side of campus, and we had the two rooms linked through Skype. So like in the other room there was no instructor. There was just a couple of TFs, and then in the main room there was the instructor, and that kind of worked. It didn't really. There were a lot of problems.
I guess I was just wondering if there would be pressure from the administrators to say this isn't going to count as a full thing towards your workload because you've already prepped it and you're not really doing the work anymore. You don't have to give any lectures.
Yeah, except that the contact hour is still the same. I mean the instructor is still there for, maybe not in all the rooms, but yeah, like the time is still.
But I'm asking, are they really needed there? Wouldn't a bunch of good TAs suffice?
I mean, so if I were to compare myself as an instructor to Eric, like I would take Eric any time, like the experience level I think is vastly different. So yeah, I think it's much better with the instructor. Yeah. Yeah.
You mentioned that you had modeled the facilities of the room on the MIT classroom, which has the really integrated tech, and then you said you guys went really, really low tech, but you say you're doing 50% simulation, you're doing online quizzes with tablets. Is this all bring your own laptop and
Right.
it's on the students
Yeah, the room is low tech. The course, I guess, does have a lot of elements of technology, but the room is like, there's nothing. There's nothing. There's
How much
just outlets.
of your time is troubleshooting everyone else's technology on?
So we only use the two systems, the NB, which there's no problems with. It's like it's managed completely through that group at MIT, and it's that easy. And then the learning catalytics, which again, has some glitches, but so I think because we don't have a million different systems, the technology doesn't seem to be an issue.
But what if their laptop is crashing or something?
Yeah, so then, it's a problem, but that usually doesn't happen. Any